Welcome back to my course. In our previous session, we explored the concept of caching and delved into its various types, understanding how it plays a crucial role in system performance and scalability. If you missed that session, I highly recommend watching it first to build a solid foundation before diving into today's topic. Let's get started and take your learning journey one step further. In today's fast-paced digital landscape, having instant access to data is crucial. Caching strategies are the secret sauce that ensures your application's data is always available, lightning fast, and seamlessly updated. These strategies determine how data is stored, retrieved, and updated between the application, cache, and database. Choosing the right strategy can significantly enhance your application's performance, balancing consistency, latency, and operational load to meet your specific needs. Let's start with cache aside, also known as lazy loading. Imagine this scenario. Your application needs some data. It first checks the cache. If the data is not found, we call it a cache miss. At this point, the application goes to the database to retrieve the data and then updates the cache for future use. It's flexible and widely adopted in most caching implementations, almost 80% of them. Can I tell you something? Have you ever noticed how websites load faster the second time you visit them? That's cache aside in action. Now let's move to the next strategy: read through and write through. Now let's talk about read through. Let's see how it works. Instead of your application directly fetching data from the database, it interacts only with the cache. If the data is not in the cache, a cache miss, the cache itself fetches the data from the database and serves it to the application. This is important to keep things simple for your application because it doesn't have to worry about managing cache misses. Everything is handled seamlessly by the cache. Think of it as having an efficient middleman who knows where to find what you need. Next, let's pair it with its sibling strategy, write through. When your application writes data, it doesn't just update the cache. It also writes the same data directly to the database at the same time. This ensures that the cache and the database are always in sync. It's great for scenarios where data consistency is crucial, like in inventory systems or financial transactions. Think of it this way: every time you save something, both your quick access notepad, the cache, and your official record book, the database, are updated simultaneously, no discrepancies. Now let's move on to the next strategy, write back. This is also known as write behind. Here's how it works. When your application writes data, it first updates the cache. The cache then takes care of updating the database, but it does this asynchronously, in the background. It's ideal for systems with high write operations because it reduces the load on the database. By batching updates or delaying them slightly, you get better performance without overwhelming the database. However, there's a catch. Since the database is updated later, there's a risk of losing data if the cache fails before the update is completed. Think of it as jotting down notes on a sticky pad before copying them into a formal document later. Let's move on to write around. Here's how it works. In this strategy, the application writes data directly to the database, bypassing the cache entirely. The cache is only updated when the data is read again by the application. It's particularly useful for scenarios where write operations are frequent, but read operations are relatively rare. This prevents the cache from being filled with data that might not be accessed often. However, there's a trade-off. If the data is read immediately after being written, there will be a cache miss, which could lead to slower response times. Think of it like writing something directly in your main notebook, skipping the sticky notes, only to come back to the notes when you actually need to refer to that information. Next, let's explore a widely used technique, time to live, TTL. Data in the cache is stored with an expiration time. Once the TTL expires, the data is automatically removed from the cache. If the application needs that data again, it will fetch it from the database and reload it into the cache. Are you wondering why is this TTL important? It's great for managing data that changes periodically or becomes stale over time, like user sessions or real-time stock prices. Let's look at this with an example. Think about DNS, domain name system, resolution. When you enter a website address, a recursive DNS server will query the authoritative name servers to get the correct IP address. The authoritative name server sends the IP address back, and the recursive DNS server caches it for a certain period. This caching period is controlled by the TTL value set by the authoritative name server. Why do you think TTL is important? Once the TTL expires, the cached IP address is considered outdated. The next time you visit the site, the DNS server will have to query the authoritative name server again to refresh the cache data. This mechanism helps prevent outdated information and ensures that the system is always using fresh data. So, in a way, TTL works like an expiration date for your cache data, keeping things current. Let's recap everything we've learned about caching strategies. We started with cache aside, where the application checks the cache first, retrieves data from the database if it's not found, and updates the cache for